Hello friends, this is your stat sir, your Ravishankar sir. ఈ వీడియోలో క్లాస్ స్టార్ట్ చేయబోయే ముందుగా మన మంచి మాట. ప్రతి మనిషికి తను చేసే పనిలో ఒక ప్రత్యేకమైన శైలి ఉంటుంది. సో మై డియర్ ఫ్రెండ్స్, నువ్వు చేసే పనిలో 10 మందిలో గుర్తింపు పొందాలి అంటే నీకంటూ ఉన్న ప్రత్యేక శైలిని కనబరచు. తప్పకుండా 10 మందిలో రాణిస్తావు, ఉన్నత శిఖరాలను అధిరోహిస్తావు. With this, I would like to start the second part of third unit, that is stratified random sampling. So in this part, we are going to discuss about two basic important theorems and the concept of proportional and optimal allocation. So in the part 1, we were discussed about the basic definition of stratified random sampling as well as the notations and terminology of the stratified random sampling. So in this part 2, we are going to discuss about two basic important theorems and concept of proportional and optimal allocation. So first, theorem number 1. The mean of the stratified random sample y bar st is an unbiased estimator of the population mean capital Yn bar. That is, we need to prove that expected value of y bar st is equal to Yn bar. By the definition of the unbiasedness, we need to prove expectation of y bar st is equal to capital Yn bar. So to prove this theorem, consider the stratified random sample mean y bar st, which is given by the formula 1 by capital N into summation I is equal to 1 to k capital Ni into Yni bar. Where Yni bar is the mean of the sample drawn from the ith stratum. Where Yni bar is the mean of the sample drawn from the ith stratum. So here in stratified random sampling, all the samples have been drawn from the subgroups by using simple random sampling without replacement. But already in the previous unit, we saw that in simple random sampling without replacement, the sample mean is an unbiased estimator of the population mean. So, since the sample of size small ni is drawn using simple random sampling without replacement from each of the stratum, we know that expectation of small Yni bar is equal to capital Yni bar. Because in simple random sampling without replacement, the sample mean is an unbiased estimator of the population mean. So now consider expectation of y bar st is equal to expectation of 1 divided by capital N into summation capital Ni into Yni bar, which is the formula for y bar st. So in place of that is equal to 1 by n into summation I is equal to 1 to k capital Ni into expectation of Yni bar. So in place of expectation of Yni bar, we are replacing capital Yni bar because expectation of Yni bar is an unbiased estimator of the population mean. So expectation of Yni bar is equal to capital Yni bar, and the formula 1 by capital N into summation Ni into capital Yni bar is the formula of capital Yn bar. So therefore expectation of y bar st is equal to capital Yn bar, so that sample mean stratified random sample mean is an unbiased estimator of the population mean. Theorem number 2. With the usual notations, prove that variance of y bar st is equal to 1 by capital N square into summation I is equal to 1 to k capital Ni into Ni minus small ni into Si square divided by Ni, which is equal to summation I is equal to 1 to k of 1 by small ni minus 1 by capital Ni into Pi square into capital Si square. To prove this theorem, since the sample in each stratum is drawn using simple random sampling without replacement, hence we have variance of small Yi bar, that means variance of the sample mean using simple random sampling without replacement, is given by the formula 1 divided by small ni minus 1 divided by capital Ni into Si square. Because in the previous unit we saw that in simple random sampling without replacement, variance of Yn bar is equal to 1 by small n minus 1 by capital N into capital S square. So here we need to compute the variance of sample mean for each stratum. So the sample mean for each stratum is denoted by Yi bar, so that we will get the formula 1 divided by small ni minus 1 divided by capital Ni into Si square. We treat this equation as equation number 1. Now consider variance of y bar st. Variance of y bar st is also can be written as summation I is equal to 1 to k pi into small Yi bar. We saw this in notations and terminology part in the last video. So that is equal to summation I is equal to 1 to k variance of pi into Yi bar, that is equal to summation I is equal to 1 to k pi square into variance of Yi bar, because variance of Cx can be written as C square into variance of x. So here in place of C we are having pi, so pi square into variance of Yi bar, that is equal to summation I is equal to 1 to k pi square into variance of Yi bar can be written as 1 by small ni minus 1 by capital Ni into capital Si square from equation 1. That is equal to, here small pi means nothing but capital Ni divided by capital N. When we substitute this pi in this equation, we'll get summation I is equal to 1 to k capital Ni square divided by capital N square into 1 divided by small ni minus 1 divided by capital Ni into capital Si square. That implies summation I is equal to 1 to k capital Ni square divided by capital N square into, when we take the LCM for these two, this can be written as capital Ni minus small ni divided by small ni into capital Ni into Si square. That is equal to 1 by capital N square, because there is no ith term in this capital N square. So 1 by N square into summation I is equal to 1 to k. 1 capital Ni will be cancelled from this. So capital Ni into small ni minus capital Ni minus small ni into capital Si square divided by small ni. So we get this 1 by capital N square into summation I is equal to 1 to k capital Ni into capital Ni minus small ni into capital Si square divided by small ni. Hence the proof. So the next one is allocation of sample size. We observe that the variance of sample mean depends on small ni, the sample size for the ith stratum, which can be fixed at all. The allocation of the sample sizes for different strata is done in the following two ways. The first one is proportional allocation and the second one is optimum allocation, because here in stratified random sample we are selecting the sample from each stratum, that means each subgroup, so that for each subgroup the sample from each subgroup will have different sample sizes. So we need to allocate those sample sizes which are very important in this stratified random sampling. So we can allocate those sample sizes by using any of the following two methods. Those are proportional allocation and optimum allocation. So proportional allocation means allocation of small ni's to various strata is called proportional if the sample fraction is constant for each stratum. That is, small n1 divided by capital N1 is equal to small n2 divided by capital N2 is equal to and so on is equal to small nk divided by capital Nk, which is same as summation ni divided by summation capital Ni by using component on dividend rule. So summation ni is nothing but small n and summation capital Ni is nothing but capital N, so which is equal to small n divided by capital N, which is a constant. So already in the previous unit we saw the definition of the sample fraction. The sample fraction is nothing but the ratio between the sample size and the population size. So here for each stratum the sample fraction should be constant in proportional allocation. So that n1 small n1 divided by capital N1 is equal to small n2 divided by capital N2 is equal to and so on is equal to small nk divided by capital Nk, which is same as summation small ni divided by summation capital Ni, which is equal to small n divided by capital N is equal to C. So that implies small ni divided by capital Ni is equal to constant, which is same as small n divided by capital N. That implies small ni is directly proportional to capital Ni. Small ni is directly proportional to capital Ni. So thus, in proportional allocation, each stratum is represented according to its size. So in proportional allocation, the variance of y bar st is given by, so y bar st in proportional allocation. So that's why we written here as variance of y bar st prop. Prop means in proportional allocation. So that is equal to 1 by n square into summation I is equal to 1 to k capital Ni into capital Ni minus small ni into capital Si square divided by small ni. That is equal to summation I is equal to 1 to k capital Ni divided by capital N square into capital Ni divided by small ni minus 1 into Si square. So that is equal to summation I is equal to 1 to k pi divided by capital N into this capital Ni divided by small ni can also be written as capital N divided by small n. So in the previous slide we got that small ni divided by capital Ni is same as small n divided by capital N. So that implies when we reverse these fractions, small capital Ni divided by small ni is equal to capital N divided by small n. So we substituted capital N divided by small n in place of capital Ni divided by small n. So that is equal to some 1 by small n into 1 by small n minus 1 by capital N into summation I is equal to 1 to k pi Si square, which is the formula for variance of y bar st in proportional allocation. Therefore, variance of y bar st in proportional allocation is equal to 1 divided by small n minus 1 divided by capital N into summation pi into capital Si square. And the second one is optimum allocation. Here optimization means either maximization or minimization. So another guiding principle in the determination of the small ni's is to choose them so as to, the first one is minimize the variance of the estimate for fixed sample size small n and fixed cost. Second one, minimize the total cost for fixed desired precision. So here in both the cases we are minimizing either the variance of the estimate or the total cost. So here minimization or maximization means optimization. So in this optimization, optimum allocation, we need to select the small ni's in such a way that to minimize the variance of the estimate or minimize the total cost. So the allocation of small ni's to various strata in accordance to with the above principles is known as optimum allocation. Thus, in optimum allocation, ni's are to obtained such that variance of y bar st is minimum for fixed sample size. Variance of y bar st is minimum for fixed total cost. And total cost is minimum for fixed value of variance of y bar st. Because that is the desired precision. So, in this optimum allocation, in the previous slide we talked about the total cost. So, we need to define the cost function. So, in any sample survey, the value of the information on the experimental units must always be balanced against the cost of obtaining it. In stratified sampling, it may cost more to obtain information about a sample in one stratum than in another. In any sample survey, the value of information on the experimental units must always be balanced against the cost of obtaining it. In stratified random sample, it may cost more to obtain information about a sample in one stratum than in another. So, in stratified random sampling, the collection of the data from each subgroup or from each sample drawn from each subgroup depends upon the cost. So, the cost to obtain the information in one sample may be more than the cost to obtain the information from the other sample. So, for example, interviewing people in rural areas is going to be more costly because of travel expenses than interviewing people in urban areas. Thus, in its simplest form, the cost function C, the cost function is denoted by C in stratified random sampling may be given by the linear model C is equal to A plus summation Ci into Ni, where A is the overhead cost and Ci is the cost per unit in the ith stratum. Obviously, Ni is the sample size of the ith stratum, of the sample drawn from the ith stratum. So thank you for your patience listening. In the next video, we will see more theorems in stratified random sampling using optimum allocation. Once again, thank you very much.